My goal in this video is to show the radius of nth Bohr orbit, the derivation of this equation. I looked it up in my physics book and it explained that there were substitutions, but it did not go through step by step. And that's what I'm going to do in this video, is show out each of those steps because I found it super helpful and enlightening. So hopefully you do too. There's three equations that we're going to start with. We're going to start with Newton's second law, F equals ma. Coulomb's law, since there is the electric charge, the attraction between the electron and the proton. So we've got Coulomb's constant times charge 1 times charge 2. We're eventually going to replace these Q's with the charge of the electron. So these are going to get replaced with E's, just a heads up. And then third, since we do have centripetal acceleration, then we're going to use that as our acceleration part for this formula. So right away, you could pause this video and you're going to use equation 2 and 3 and substitute for F and A. Assuming that you've taken a moment to do that, we'll do that together right now. So we're going to start with Newton's second law. And again, use Coulomb's law to replace, since we know that that is the force, that electrostatic force between those two. But like I said, we're going to just at this point replace these charges now with the charge of the electron. So E times E. Our distance between our two charges is in fact R, so we could just leave it as that R squared, as it's an inverse square law. And then our mass stays the same, which is the mass of the electron. And then multiply that all by the velocity, the linear velocity squared divided by the radius. Okay, now at this point we're just going to solve for r. You could pause the video again and do that on your own, but you can already see what we're going to do. We're going to multiply the r squared over to the right, divide the mv squared over to the left. So we got k e squared, combine those two, divide the mv squared to the left, multiply the r squared over, and we're at a good point to stop right now because what we have is very good. However, there's no quantization happening. And so this is where we're going to use de Broglie's wavelength equation. So let's call that number 4 over here. Write that out. I used to tell my calc students that when you didn't know what was happening in a math class, it was just often substitutions that they didn't tell you about. All right, so we've got the wavelength, Planck's constant, divided by the momentum. The wavelength we could consider as some integer number of wavelengths. And so we know that it's going to be some function of the circumference itself. So we could replace the wavelength with the circumference, 2 pi r. There's going to be some integer number of them, so I'm just going to introduce that on the right side here. So n is that integer number of wavelengths times h. And then we could just substitute for p, the definition of momentum, right? So we could just do m times v. So far, so good. Let's put a box around this because we're going to use this to isolate two different variables. The first one that we're going to isolate actually is over here. We're going to replace this r, and we're going to use this new equation to do so. So let's divide that 2 pi over. And so r is nh over 2 pi mv. So we could call this one number 5. And that's what we're going to now replace for r here. Keep the left side. So now it's starting to look like the equation that we knew we were trying to get. But we notice, okay, these things need to be squared. What's going to happen? Are we going to have to square both sides? What's going to take place next? Well, all right, let's pause before we even go any further, and let's just cross multiply this. Let's simplify this just a little bit. We have an m, so these things are going to cancel. And then let's multiply that 2 pi v to the left. Let's multiply that v squared over to the right. And you might have already seen it, but we could cancel one of the velocities on the left with one of the ones on the right. And we've gotten this far. However, if you look closely again at that equation of the radius of nth Bohr orbit, you'll notice that it's not a function of velocity. So now we need a substitution for this. And you could use either this equation or equation number 5 to isolate v. In fact, let's just use equation 5 and let's interchange r and v. We'll call that equation number 6. 2 pi mr. Sliding off my table there. So that's 6. And then let's use it's just substitution mayhem, isn't it? I mean, how many substitutions have we done so far? I don't know. Okay, 2 pi times k times e squared equals nh. Here we go, because now finally we see we got n and h, and that's going to multiply with this n and h. That's going to get them to square. That's a good thing. It might look at first glance like, oh shoot, these 2 pi's are going to cancel, but they're not, right? Because we could divide that 2 pi over and then we get 4 and pi squared. That's another good thing. That's just another step closer to where we want to be. So I'm kind of running out of space here, so let's just jump up to the top. Again, I'm just circling all the variables that we're isolating. We're isolating r here. So let's go ahead and multiply that r over to the left side, and we'll divide that 2 pi k e squared to the right side. So we've got r, and let's go ahead and multiply these two together first. So n squared, h squared up top. And then we're going to divide that 2 pi down here. So 2 and 2, we're going to get 4. Pi and pi, we get our pi squared. So far, so good. Divide that k, divide that e squared over. And then finally, we have that mass. And at this point, hopefully, that looks familiar and maybe even somewhat satisfying that we were able to piece our way through that derivation, one substitution at a time. And we could use transcript n to indicate each orbital. Now, let's suppose that we use n as 1, and notice again we can just replace a lot of these things are just constants, and so Planck's constant, Coulomb's constant, the charge of an electron, the mass of an electron. If you looked up in a textbook, so I just looked up in my textbook, R1 would have a radius of 5.29 times 10 to the negative 11 meters. To me, that's the most satisfying part, because I asked in my phone, Siri, what is the radius of a hydrogen atom? And the answer 53 picometers, which is the exact same thing as what we got. So finally, one last descriptor. We could double this and end up getting the diameter of a hydrogen atom. Double to get the diameter of a hydrogen atom. It is amazing to me that we can use these basic equations from physics 1, Newton's second law, Coulomb's law, centripetal acceleration, and just one newer equation in this beautiful combination to determine something absolutely mind-blowing. Hopefully you found this video helpful, and I'll see you in the next video.